Hello everyone. Here we will study some applications based on Gauss law. Before taking up that derivation, we will define certain terms. The first term is called as linear charge density, which is denoted by lambda. By definition, lambda is defined as charge by length. So its SI unit would be coulomb per meter because it is charged by length. The next term is called as surface charge density. For that, the symbol is sigma. Sigma is defined as charge by area and its SI unit would be coulomb per meter square. The third term is called as rho, and rho is defined as charge by volume, and for this the SI unit is given by coulomb per meter cube. Now lambda, sigma and rho, these are useful if we have a very big charge distribution. That is, if you have a very long charged wire, or if we have a very big charged area or a charged volume. In that case, if you want to find the charge in a given region, for example, think of this wire to be infinitely long. If this charged wire is infinitely long, then you want to find the charge only in some part of it. If you want to find charge only in this section of the wire, then we can find what is that from this equation. So charge in this section of the wire, if we call that as Q, the charge would be given by lambda into length. So lambda, sigma, rho are useful to find charge in a small elemental region or a small area or in a small volume. Now in this case also, if you think this area to be very big, and then if you want to find charge in a small region, if you want to find charge in this region alone, then if the charge is called as Q, that Q will be given by sigma into area. So lambda, rho, sigma and rho are useful to find charges when the distribution of charge is very large. Now we'll use Gauss theorem to find electric field due to a point charge. Now we already know what is the electric field due to a point charge using Coulomb's law, from which we obtained the electric field due to a point charge. For example, if the charge here is Q, and if we have to find the electric field at a given point, suppose this point is say P, we want to find the field at this point P at a distance of r from the charge. In that case, the electric field is given as K Q by r square. We have already obtained this using Coulomb's law. I will try to obtain the equation for electric field using Gauss theorem. The purpose is to understand how to use Gauss theorem, because in this case, for a point charge, it is easy to find the electric field by using Coulomb's theorem only, but we need to find as to how to use the Gauss theorem. And to start off with, we'll take for a point charge. The first point is, suppose imagine we have charge capital Q, and then our aim is to find electric field at a given point. We want to find the field at this point P, or we'll call it as A to differentiate Q and P. At this point A, suppose if we need to find the electric field such that the distance between point Q to point A is some small r. We want to find in this case. Then what we can do here is, in this case, we need to choose a Gaussian surface. Recall that Gauss theorem tells us the total electric flux is equal to the charge enclosed by epsilon naught. This is from Gauss theorem. This is what the Gauss law tells us. But recall what is phi itself is defined as. By definition, phi itself is given as integral of E into dA into cos theta. And since we are finding for a closed surface, because Gauss theorem is true for a closed surface, we can take integration over the entire surface. So the circle around the integration symbol indicates that we are integrating over the entire surface. Now here there are three terms. There is E, there is dA, there is cos theta. Now it is difficult to integrate all three together. So we need to integrate with only one term and we need to pull out two terms out of it. So what we can do is we can choose the Gaussian surface in such a way that the electric field remains constant on the Gaussian surface. So in that case, if the surface is such that at all the points, if the electric field remains constant, then from this integrations E comes out. So this is taken care of, and if we ensure that cos theta is either a constant or equal to 1, so by making cos theta equal to 1 or constant, in that case both E and this comes out of the integration, and then what remains would be phi is equal to E comes out, cos theta comes out, and what remains would be just integrate dA. Now this is now easy to integrate. The first point is always ensure that you take a Gaussian surface such that the integral becomes easy to solve. For that, to obtain these conditions, we should find symmetry in the distribution of the electric field. So in this case, by common sense, we can take a sphere around this charge distribution, because for this point charge, the best fit curve, the best fit Gaussian surface would be a sphere. So let's draw a sphere around the point charge and also ensure that the Gaussian surface is passing through the point charge. So let's draw the sphere. We have drawn a sphere as shown. Now at all the points on the sphere, the field would be constant, because every point on the sphere, it is a circle in 2 dimensions, because we can't draw 3D in the 2-dimensional plane. So basically it is a sphere seen as a circle in 2 dimensions. At any point on this sphere, it's a point B or a point C or a point D or a point E, for any point on the sphere, the distance from the center where the charge is placed remains same. So in this case, E would be a constant. And also here, what is happening is, if we look at a small region somewhere here, a small region here, whose area would be dA. So don't get confused with this A and dA. dA would be the area vector. So at this point, we saw in the previous lectures that for a given point or for a given small elemental area, the area vector would be always normal to that elemental area. So for the small area on the sphere, the area vector would be normal to that sphere. And also we have learned that for a point charge, electric field always goes out radially. So from this point, electric field goes out radially. So by taking a sphere, we have ensured that the electric field as well as area vector are in the same direction. Now this is true for any area on the sphere, which means if we take a small region here also, a small part here, at this point also, you would realize that the area vector for the small part would be going out normally to that point. So the area vector would be normal to that point. It's like this. It goes out normal to that point. Similarly, electric field also from here would go out normally only. it goes out like this. So again here also the angle between E and dA is 0. So what we're finding is, we're finding for any elemental area, whether it is here or wherever it is, at all the small regions, the angle between the electric field and area vector is 0 and cos 0 is equal to 1. So in this case, sphere is the best Gaussian surface. Suppose instead of a sphere, if we take, say, something like a cuboid, we have point charge here, capital Q, and if we take a cuboid as the Gaussian surface as given here, something of this form, then what happens here is, if we take any small elemental area, for example, for this elemental area, the area vector is normal to this point, it goes like this. And also at this point, this is the elemental area dA, and also at this point the electric field will be going out radially only. So for this elemental area, the angle between E and dA is 0. So it is fine in this elemental area, but if we take some other area here, for this point also, the field would be normal to this point, because when the area vector is normal to that point, because at every point the area vector is normal to that given elemental area, but the field from here will go out radially, it goes like this, it goes like this. So the angle between the electric field and area element is not 0 now. So the angle made here is 0, it's something else. So if we take different areas, the angle made by the electric field and area vector would be different. And also observe carefully, the distance from this charge to this point is not same as this distance. In fact, the distance from the charge to this point here is greater. So in this case, even E is not constant, because for different points on this cube, the field will be different and also angle is varying. So here cube is not the right Gaussian surface. You can still do it, but the integration becomes very complicated. So to avoid those problems, take a simpler Gaussian surface. Now let's begin the derivation. The electric flux by definition is given as integral of E into dA into cos theta. In this case, since we are integrating over the entire Gaussian surface, I put a circle around this just to indicate that the integration is over the entire closed surface. Now here flux is equal to E comes out because E is constant as discussed earlier, and then what remains here would be integration of dA. Here theta is equal to 0 because for any region on the sphere, the angle between electric field and area vector would be 0, and cos 0 will be equal to 1. This is equal to total electric flux is equal to E into, now this is a total surface area because we are integrating all the small elemental areas. So what we get would be the total surface area, which is E is equal, phi is equal to E into 4 pi rs, 4 pi r square basically. We will call this as 1. Now let's recall what is flux from Gauss law. So from Gauss law or Gauss theorem, we know that the total electric flux is equal to the charge enclosed by epsilon naught. In this case, this Gaussian surface, this is the Gaussian surface. Here, this Gaussian surface is enclosing only one charge whose value is capital Q. So this is equal to capital Q by epsilon naught. We call it as 2. Now equating 1 and 2, do remember that This flux is obtained from definition of electric flux, and this flux is obtained from Gauss law. Equating 1 and 2, what we get is E into 4 pi r square is equal to capital Q by epsilon naught. If you bring 4 pi r square to the right hand side, then E is equal to Q by 4 pi epsilon naught into 1 by r square. As seen earlier, this is what you obtain for a point charge also. So the idea here is to see as to how to use Gauss theorem. In terms of vector form, electric field is equal to Q by 4 pi epsilon naught into 1 by r square. Electric field goes out radially as seen earlier also, so it will be into r cap. So this is the required form for electric field due to a point charge.